Oh, hello. So I had a good time this summer working with Daniel. He was assigned to me because I'm an observational astronomer and I mostly do visual observations, not X-ray, not infrared, none of that. So we used the GORT telescope, and I asked him what kinds of projects he would like to do. GORT can do imaging, so photometry or astrometry, and he said he would like to learn more about gravity and track an object and determine its orbit. And so that's what he did. We got some observations, measured the positions, and used those to determine the orbit. And I'll let Daniel say how that worked.
Hello, everyone. My name is Daniel Cheng, and this is my summer internship presentation. Okay, this summer, Dr. McLean and I observed an asteroid called Artemis, and we used a robotic telescope to get digital pictures to determine the position of the asteroid, and we used those images to find the orbit of the asteroid. In order to track the position of an asteroid, we use the Minor Planet Center website to find an asteroid to track. Some history for the asteroid I chose. 105 Artemis is a mean belt asteroid that was discovered in 1868, and it was named after Artemis, the goddess of the hunt in Greek mythology. Okay, so in order to find the orbit of the asteroid, we have to use the coordinate, the space coordinate system, also known as the celestial coordinate system. And in this type of coordinates, we have the right ascensation, or known as RA, and the declination, or known as DEC. So yeah. So this field is also known as astrometry, which is the branch of astronomy that deals with the measuring the position of the objects in the sky. It is used to determine the coordinates of objects that are newly discovered and are moving across the sky. And here, as you can see, the RA units are hours, minutes, seconds, and the declination units is degree, minutes, seconds. Okay. So to find the exact orbit, the most of a very common method to use is the Gauss method, and the Gauss method requires at least 3 observations, and from these 3 observations we can get 6 independent variables, and using a system of 6 equations we can determine the exact orbit of the asteroid. Most of this is done with using a program on a website or coding in Python, and so yeah. But I think before the computer was seeing, people would do them by hand. Okay, and just so to a few more history. For the orbit is a list of orbital elements. One is, so around this image, I don't know if you can see it well, but there's the semi-major axis, the size of the orbit. There's also the E, which is the orbital eccentricity related to total angular momentum. Then there's also the orbital inclination, which is the angle with the elliptic plane right here. And this also omega, the longitude of the ascending node, and the angle between the vernal equinox and the ascending node of the orbit. There's also the argument of periapsis angle, which is the angle between the ascending node and the periapsis point in the asteroid's orbit. And there's also finally there's a time, which is the basically time for the asteroid to take, I think. All right, okay. Now with that out of the way, here's the basically the exact process that we took to take the pictures and use those pictures to determine the orbit. To take the pictures, we used the GORT Observatory. Here are some snapshots of the image. This is the basically the workspace where you can see the current the programming process. A bit below there is where you can input the time to take the image. Here's this some other stats with the program, and when the program is finished, you can get a list of images below the on the bottom of the website web page here. Many of those images have a file type known as FTS, which is what I'm going to get in the next slide. So to open up the FTS files, you have to use a program known as Astro Image J, and this program allows you to open up these images and see the image. And on the image, there's basically a lot of stars around where the image is taken, and there's not really much to that other than you can also see the right axon, the I and the DEC coordinates on the image. But we have to find an asteroid right here, and it's gonna. So how do we find the asteroid out of the many stars in this image? So we can use another image analysis software known as Aladdin. Aladdin is a set of images, basically a set of images that represents a large part of the night sky and space. And basically what I done was that I got the picture taken, and then I input the coordinates of the picture into the Aladdin software, and this allows me to locate the exact position where the image was taken. Now, because the asteroid moves constantly and is not always in the frame, that means that it's very likely that an asteroid is not going to appear on the image that is taken, the image on Aladdin, because Aladdin is a set of images taken in a long period of time. And using this fact, we can compare the image in Astro Image J with the exact same spot in Aladdin, and the difference between the two images is where the asteroid is located, because the asteroid will locate on the image we've taken, but will not appear on an image taken at a different time. As you can see here, we can see a clear difference that this is an asteroid, because this is nowhere to be found in the other image. Okay.
I know, I'm just going to give you a gentle poke that we've been presenting for 8 minutes so far.
All right.
Just move you along a little bit more quickly. Thanks.
Okay. So once we have once we have gotten data down, we could input them into a 80-column MPC format. Here you can see is the date and time, and here's the coordinates of the asteroid. And by inputting these data into a software known as online final orb, we could get the data as well as the entire orbit of the asteroid. And there's also the orbital elements that is resulted from our data, and comparing them to the official elements for 105 Artemis, the values are very close, meaning that our project was a success because our result is very accurate to the official results. Okay, I kind of want to go to that, but here's basically an animation describing the orbit of 105 of the asteroid that I calculated to find. And yeah, okay. There's also a lot of other things you can do with the orbit simulator, as you can see here. Okay, so as a conclusion, for future work, these calculations can be proved to be very useful in determining the orbit of other asteroids and most importantly, discovering if any are on a collision course with Earth to cause a mass extinction event. And another measurement that future work can take place is that we could calculate the brightness, measure the brightness of each of the asteroids and to determine what they are made up of. The 105 Artemis is very dark and is composed of mostly carbon material. So, but there are other asteroids with different types of brightness. And so as a conclusion, by taking the image of the asteroid and taking the coordinates of these by taking the celestial coordinates of the asteroid, we were able to find a very accurate orbit that can tell us where the asteroid is going to travel in the future. And through our data and our results, we could say that this project was a very accurate and yeah. So, and as an acknowledgement, I would like to thank NASA's new Diversity Network Program, Professor Lynn Komsky, Professor Kevin McLean, and all the staff in the Neurodiversity Network team. Thank you for listening.